Hey friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 438. Find all anagrams in a string. In this video, we are going to explain two methods. The first one is based on sliding window, and the second one is based on hashing, or we can say we use bit mask. So first, I'll read through the problem statement to digest the task, and then we do an analysis of the ideas, and finally we share the different formats of codings. First, the statement. Given two strings S and P, return any array of all the start indices of P's anagrams in S. So we may return the answer in any order. So here the second paragraph explains what's an anagram. So here are two examples. Let's look at example 1 to gain some feeling. So here P is the ABC, that is A appears once, B and C also appear once, respectively. So here, if we start from index 0, we see CBA. So it's actually an anagram of P. So we include the index 0 in the output. So also, if we see here BAC, it's another anagram with respect to P. So we include this 6. So for this problem, the output will be 0 and 6. So before we look at the solution ideas, let's also look at the constraints. First, the two strings S and P are bounded below by 1. So in length, it means they are both non-empty, and bounded above by 3 times 10 to the power 4. So this number, we are going to use it in some fashion in the hashing solution. Secondly, S and P consist of lowercase English letters. So this assumptions actually plays some role, and some maybe important role in the coding format, which we will make it clear. So with that said, let's look at the two methods. So the first method is based on sliding window. So the first method is routine, and we will go over this format of solution first. So here, let's do this. So first, I'm going to make a reference dictionary. So this is collections counter. So basically, we count the unique characters in P and their frequencies. So this is our reference. So when we do linear scan using sliding windows, if we find the dictionary, running dictionary matches the reference dictionary, then there's a match, right? So first I'm going to get M and N. So M is the length of P and N is the length of S. So ideally we hope that M is less than or equal to M so that we could possibly match P. So first I'm going to get a current, that is collections counter. So I'm going to use the first M characters in S. So first let's make a check. So in order for that, let me initialize a result, which is a list, which is going to hold the starting indices. So first, if current equals a reference, as you may notice that this requires comparisons of two dictionaries. So if so, we are going to append index 0, right? So otherwise, let's make a for loop. So for I in range M up to M, then we are going to move towards the left one character. So in other words, the current is going to increment the occurrence of letter SI by 1. So similarly, it will going to decrement this letter M characters before by 1, right? And then we need to compare if current equals reference. If so, we are going to append the index. So here I will be the ending index. So let's add the starting index, that is I minus M plus 1. And then afterwards, we can return the result. So before we present other solution formats, let's first make a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic cases, but it's a little bit slow. So now with the intuition built so far, let's look at the second solution formats. So here I'm going to copy this function signature, and I'm going to change this one to be version v1. So now let's look at the idea for the second solution method. So the second method is in idea similar as the rhyming cup pattern matching algorithm. What we do is to design hashing of the pattern P, and then we compare the hash value when we scan the string S. If the hash values are equal, then the patterns match. So the key idea here is to design good hashing, and the pattern is, as the pattern is of anagram, then the position of a letter in the pattern P is not important, and therefore the hashing of P shall be permutation invariant with respect to the indices. So meanwhile, notice that there are 26 lowercase English letters. So here we are using the second constraint atom, and the length of S or P is bounded above by 3 times 10 to the power 4. So actually we can estimate the bit positions needed if we want to do bit masking. So this is bounded by log 2 of this number. Then we can know that this number equals log 2 3 plus 4 times log 2 10, because log 2 3 is less than 2 and log 2 10 is less than 4. So overall this number is less than or equal less than actually 2 times 4 times 4, that is 18, and therefore we could make a hash table as below. So for a character in the, let's say in ABCD XYZ, so we can hash this value to be 2 to the power 19 times I. In other words, we want the character at index I in the alphabet takes on at this bit position, that is 19 times I. So this separation will make sure so our hashing method will work. So if you like, you can see this I is ordinary number of character minus 97. So that's a technical detail or another viewpoint. So now the hashing value of P will be the sum of the hashing of the characters in P. So if a substring in S has the same hashing value as P, then they must be anagrams. So notice that the bit positions of alphabet are well separated. So this design makes the conclusion sound. So in other words, so we are using the hash value in essentially encoded which letter appears and how many times it appears. So similarly as the dictionary, but in a very compact form or encoded format. So here is an extension. So you can check out the rhyming cap algorithm and a related algorithm called KMP algorithm, the Kuss-Morris-Pratt algorithm. So with that said, let's look at the coding. So first, I'm going to write the hash. So in order to be precise, so we can do this. Let's first do this alphabet. So I'm going to use this S union this set of P. These are the unique letters involved. Then I'm going to use a bit map. So here I'm going to letter. So we're going to map this guy to 1. So we're going to use this position. So this means 2 to the power 19 times I. And so the reason we use 19 is due to the analysis here. So it's bounded by 19. Actually, this number is bounded above by 15. So essentially, you can also use 15. That's more compact. So with that said, let's see. This is a dictionary comprehension. So for I letter in enumerate alphabet. So this way, we give a encoding for each of the letters, or you can see it takes on at this bit position in a long list. So with that said, let's get the hash of this P. So here this is nothing but sum of bitmap for letter in P, right? So also let's get the first hash at this index 0, so with same length as P, so it's bitmap. So letter for letter in S. So I'm going to opt this one, length P, right? So this actually is in parallel to here, current and reference. So now let's first check. So if hash 0 equals hash P, then in this case, so let's do something like this. Let's see output. So I'm going to use this result equals empty, right? So if this two the same, so we're going to append 0, right? And then we are going to iterate over the S. So here we can see, so as we see, and let's check this one. So we're going to include E and exclude C. So after we've seen this one, we're going to include B and exclude B. So this way, actually, when we look at this, so it's so this is the one we exclude, this is the one we are including, starting from this one. So we can actually use alignment mechanism. So we're going to use zip. This is just two technical details. So then for index and for old, new, the old means the character we are going to exclude, and new is the character we are going to include in the sliding window in enumerate. So zip, so S, so then we're going to use this, right? So here we are going to using index starting from 0, right? And then so we're going to check, so then the hashing 0 is incremented by the bitmap of the new character, right? But it's decremented by the bitmap at the old character, right? And then we're going to check if hash 0 equals hash P, right? If so, then it means we get one valid match. So we're going to append. So here the index should be index plus 1. So from the, because here I'm using index 0. So with that said, so we are ready to return the result. So before we make some comments, let's first do a check. Yeah, it passes the first example. Now let's look at the generic case. So yeah, this is the this passes all the test cases. Actually, this way of writing or solving the problem is much effective in time complexity. So actually, another a comment we want to make is here we are appending idx plus 1. So actually, when we use the enumerate method, so we can instantiate initialize a starting index. So let's iterate from index 1. Then we do not need this one here. Just include this index. Let's check that. Right. So this is the correct. So this is the one comment. Another comment is here. So actually here we are using tab conversions. We convert S and P to two sets and then do union operation. So this actually can take can waste some time. So if we look at the constraint, so S and P consist of lowercase English letters. So we can actually further optimize this code a little bit. So here I'm going to call this one version v2, and then in this one I don't actually need this one. So actually we can, if we like, so we can alphabet. So we can use the A, B, C up to Z. So this is nothing but string ASCII lowercase, right? So this is the string and like A, B, C, D up to E. And then so you just use this here, and similar it will work. So let's do a check. Yeah, it passes all the test cases very fast. So with that said, I guess that's about it for this specific problem. So we are going to have some follow-up videos for problems related to anagrams. So you're welcome to follow up and check those videos out. So with that said, I guess that's about it for this video. Thank you.